This is our third video for reviewing for the Physics 12 final exam. This was a very big unit for us. We actually did 2 units in one. Half of it was looking at work and energy and power. And in the second half of the chapter, we looked at collisions and conservation of momentum. And right on the theory page here, right in the center, I've got this circled thing here that says examine the question, because you kind of have to look and go, okay, how are we going to do this? Is it about forces and distances where we might go with conservation of energy? That's a really big topic for us in physics. Is this question all about, essentially being accountants of all of the joules of energy? Or is this a story typically involving collisions where it's best to be done with conservation of momentum? And so we're going to have to take a look at each question and go, okay, what's the best line of attack for each particular question? So if it's about conservation of momentum, that one has kind of some interesting units, kilogram meters per second. So let's kind of look at the theory one half at a time here. I'm going to look on the left side and just take a look at conservation of energy. This strategy works really well for single objects that are changing height and speed. Maybe there's some forces going on there. Maybe some forces making it go faster, maybe making it go slower. And we've got this big, great organizing equation here. It's actually kind of the work energy theorem all written out nicely. We've got before and after, and the MGH terms, those are all about heights. Does your story have different heights at the beginning and at the end? Got the height at the beginning, got the height at the end of the story there. So if your object's got different heights, that's a great way to bring it into the calculations. And then we've also got a place where we can bring in speeds. Is your object going fast, whether it's at the beginning of the question on the left or at the end of the question on the right. And we can even do some work to make things speed up or slow down. The FA multiplied by D term, that's what we just called the work in term, where energy is coming in because somebody's getting tired. We jokingly called it the ALF term, right, where somebody is giving you some energy, they're donating it to you, they're losing energy, but they're giving it to you, so there's some joules of energy coming at you. Or maybe it's a force of friction multiplied by distance, maybe it's some sort of heat that's being lost. It's not disappearing, it's not being like annihilated, the energy is just going into another form, but it might be leaving your object as it goes to heat the ground up or something like that. Now this equation is great. We can even modify it if we go higher than mountains where MGH doesn't work anymore. Once you go higher than mountains, that value for little g just can't be trusted to be 9.8. It drops off pretty quick. But we can make some modifications. We can actually just take out MGH, and in its place we can put in negative g m all over r. So anytime it's a question where either at the beginning or at the end you go very high, you have to do that. We'll take them both out. Even if it's only high at the very, very end of the story, we'll take them both out and we'll put these negative g mm over r's in instead. The issue there, the reason why we have to do that is, again, because little g changes if you go higher than roughly Mount Everest, if you go higher than 10,000 meters. Another thing we saw show up in this chapter, sometimes instead of telling you about the force and the distance is just, one number for each of those, you're actually given a graph of applied force and distance, and the shape might not be a nice rectangle. But what you can do is you can find the area of whatever shape you see, and the area underneath that force applied distance curve is equal to the work in. All you have to do is find the area, and that is FA times D. So that area would equal what you'd be trying to put into your equation for FAD. Same thing if it happens to be a slowing you down force. The area here can be very helpful. It's equal to the work out. It's equal to the heat in this story. So it can be found just as an area, and then you can drop that value in for force of friction times distance. One last little bit of theory. We also did review power. Power is measured in watts. Abbreviation for that is just a capital W. The units there are watts, named after James Watt, and it's just either work or energy divided by time. It's really all about joules per second. And we actually did a couple of examples where we noticed that because work is force times distance, if you're pushing something at a nice steady speed, the power is actually the force multiplied by the velocity. I think we did a couple of questions where we were pushing a box at a nice steady speed and saw that. Okay, let's go back up to the top of this page and let's take a look at the other half of the chapter. If you've got a collision or an explosion, it's kind of the same thing really. So there's a couple of objects on the go, then the main idea is conservation of momentum. And that's where you have to add up all of the momentums originally. So you got to do that big kind of summation. That's the Greek letter that tells us we're going to do that. And you have to add up all of the final momentum values. And you're going to find that they're the same. But there's one huge catch, especially for Physics 12. These momentums, they may be two-dimensional. So you're going to have to be super careful when you add those up. So right under that, I've said, hey, is this a two-dimensional problem when you go to stare at it? And we'll try some out here in just a second. Because if it is, then you have to respect that, and you've got a couple of options. You could do components, and this means that you're going to do 2 grade 11 questions in one story. And it's really awkward. Let's be honest. Nobody liked it. That's when we would do equations that would be something like this. Mass of object 1 times the velocity of object 1 in the x direction initially plus the mass of object 2 times the velocity of object 2 in the x direction only initially is equal to, and then you just keep on going. At the end of the story, mass 1, velocity of object 1 in the x direction finally, and you would only focus on the x direction. And then you would have to do this madness all over again in the y direction. But this first equation would be nothing but x's. That's a lot of work. Hopefully you can go with option B. And that's where you do it all at once just as a vector solution. In other words, we're going to use a triangle. As long as you've only got 3 sides, right? If it had the 4 sides, then you're stuck doing the component method. But maybe you've got one object at the beginning, like a bowling ball, and it's got some momentum. So here's the momentum of object A initially. It's going beautifully sideways. Maybe the bowling ball hits some pins, and the bowling ball goes this way. So here's the momentum of object A finally, and the pin that it hits, it has momentum that goes like this. Momentum of object B finally. As long as you've only got 3 of those, then you can do a triangle, and it is really, really nice. Be super careful. We'll talk about this when we do the questions. Make sure you use P's. Don't use velocities for that picture. It's got to be momentums. You've got to be working in kilogram meters per second. In this half of the chapter, we did also talk about how you could use the idea of impulse, which is all about shoving an object. So impulse is actually just force multiplied by time. It's measured in Newton seconds, and it will cause a change in momentum for your object. Another way to calculate that is you could get right into mass multiplied by changes in velocity. You want to go one step further? That's equal to mass multiplied by final velocity subtract initial velocity, because that's how we always measure change. You could, I guess, even get a story where you're given a graph of some sort of pushing force, some sort of applied force, and time, not distance but time. Then you could find the area of that, especially if it was a weird shape. You could find the area, and that area would be the impulse. That area would be the value for force multiplied by time. You could take that area and you could actually just put it in to the equation for F times t. Okay, on the next page, you're still kind of just getting the theory ready to go. Got a kind of a bizarre example here of a Winnebago orbiting around some small asteroid. The picture is obviously not to scale. But we're just going to have a little fun with this and see if we can kind of get comfortable with all the different calculations we can do. Then we'll dive into the questions. So imagine there's this asteroid. It's got a radius of 4,000 meters. And you could have a Winnebago, driving around on the surface. Or maybe you've got a Winnebago actually up in orbit in space at a height of 1,000 meters up in the air. When we talk about orbital radius, we're always talking about going to the middle of the circle. That would be the center of the radius. So your orbital radius would be that number, all the way to the middle of the circle. Okay, well, with the numbers that are there, let's talk about the sort of things that we could calculate. Orbital radius. If you wanted to find that, we could say, hey, the orbital radius would just be the asteroid's radius plus any heights that you've got. So in this story, the asteroid's radius is 4,000 meters, the height's 1,000, so it looks like the orbit size is 5,000 meters. Somebody might say, well, what's the force of gravity on that Winnebago when you're in orbit? no problem. That was actually in the last review. Force, you could go big G, mass 1, the asteroid, mass 2, the Winnebago, all divided by how far they are apart, squared. And this is when you're in orbit. So you'd be wanting to put in the 5,000 number in for that R value there. And the force, actually, if you try this out, I think the numbers are around 32. Maybe more important than that, the units. Well, it's a force, so it's newtons. Potential energy on the surface, this is going to be a space question. So you're going to be leaving the surface. You're going to have to go and swap out the idea of MGH and go with EP is equal to negative G M M all divided by R. And if you're on the surface trying to figure this out, we're going to be putting in a 4,000 number for that. It won't be 0. You have to go put the number in. This is compared to infinity. We jokingly said compared to where the aliens live. And the potential energy is a really big negative number. It's negative 2.0 times 10 to the 5. And that would be joules because it's an energy. The velocity while you're in orbit, I talked about this in the last tutorial video. If you rearrange F net equals ma, you can get to velocity is g, mass of the asteroid, divided by your orbit size down in the bottom of that fraction. And so that's going to be 5,000 that's down there. And it turns out this velocity, it's not very fast. Just 5.17. That'll do. Meters per second. Potential energy in orbit. Got to go and use that negative G mm over R again. Same numbers as before, with one exception. If you want to do this in orbit, now you've got to put 5,000 in for that value for R, for how far you are away. And this number is still negative because you haven't got to infinity yet. That's how far you'd have to go to get to 0 energy. This number is negative 1.6 times 10 to the 5 joules. So you can see it's less, or it's closer to 0 than that negative 2 times 10 to the 5 joules. We're not quite as deep into that energy pit compared to infinity. Kinetic energy in orbit, you've actually got a couple of choices here. If you want to find EK for that Winnebago flying around in orbit, you could just do 1/2 mv squared. Nothing wrong with that. That's the way to do kinetic energy. Or if you want to be kind of sneaky and efficient, you can take half of your answer for the potential energy when you're in orbit, but you got to remove any minus signs. I'm going to put some absolute value bars there, just in red for emphasis. So the kinetic energy for that Winnebago when it's up in orbit, I can see right above this box here is the potential energy in orbit, negative 1.6. So it's half that. It's not negative though. So it's going to be a 0.8 times 10 to the 5 joules because it's half the 1.6. Now, your calculator's not going to show it like that, right? Your calculator's going to say 8.0 times 10 to the 4 joules. Whatever. It's still half. We didn't talk about this very much, but you will next year a bit. Total energy, that's going to be the combination of potential and kinetic. So if you add those two together, you're going to find that the potential energy is bigger, it's more negative, it wins, so the total energy is a negative answer. It's negative 8.0 times 10 to the 4 joules. And the acceleration of gravity at the asteroid surface, this is actually a review from the last tutorial. That's the gravitational field strength. That would be big G, mass of the asteroid, divided by the radius of the asteroid squared. It kind of looks like force, but it doesn't have another mass in there. And you would be putting in 4,000 just at the surface. This G, by the way, is really tiny. It's not as impressive as our Earth's 9.8. This number is 0.0083 newtons of weight for every kilogram. Okay, so that's it's a couple of pages of review. Let's try a couple of examples out, See if we can see how to decide whether we're doing energy or whether we're doing momentum as we look at each one of these questions. So question number 1, how much work is required to lift the Winnebago from the surface to a place infinitely far from the asteroid? We're not putting it into orbit. We're just going to do an elevator ride straight up into space. It's a space question, so we cannot do MGH. We have to actually swap these out, and we're going to be putting in negative g mm over r. At the beginning, I'm going to swap out that MGH, put negative g mm all divided by r. There's no speed at the beginning. Doesn't say we're going to take a running start at it. Doesn't say your Winnebago is going to hit a jump and go shooting up into space. You can throw that away. We are trying to find this answer here. So I'm going to say, yeah, this worked. That's what we're trying to find. At the end of the story, we're going to be infinitely far away. So when you're infinitely far away, for space questions, that's when your potential energy is 0. So we can actually take this term for potential energy, we can scratch it off. We can say, no, it's 0. We're out in space. We're not going to have any speed left, and there's no rubbing it on any surface on the way out. So, wow, this whole side out here actually just says equals to 0. So looking at last page's numbers, you have negative 2 times 10 to the 5 plus some work gets you to nothing. It looks like this answer for work is 2 times 10 to the 5 joules. In terms of the picture, you would be fighting against the force of gravity. We would actually be starting right here at the surface of the asteroid. This could be like the 4,000 meters from the center reference point. And what you've just figured out, this 2 times 10 to the 5 joules, you've just figured out the area under this curve out to forever, which is kind of strange, but it goes all the way to forever. It's just the area underneath that force of gravity curve. The second question is similar, and we're still going to be able to steal answers from the previous page. How much work is required to lift the Winnebago to an altitude of 1,000 meters above the surface? Not in orbit, just an elevator straight up into the air. So sticking with the graph here for a second, we're going to be going from, like the 4,000 meter away point out to the 5,000 meter away point. You're really actually doing an area question. The work that's involved is actually this area. Very complicated because of that curved top, but it is true. It's going to be the area underneath that curve. It's going to be less, of course, than the last answer. It's a smaller looking area. So for this, for starters, I'm going to make some changes here. This MGH, nope, got to go. That one's got to go. We've got to change that to negative g m all over r. Negative g m all over an r. You have to do that for space questions. We're not taking a running start at it. And we're not going to be finishing fast either, so I'm going to throw away the speed stories. And we're not rubbing this on anything. So it looks like we've got, I'm just going to use this line right here, we've got this negative g mm over r plus some work is equal to another negative g mm over r. I'm going to steal the answers from the last page. This one is when we're on the surface, so it's the minus 2.0, 10 to the 5 joules. Plus some work needs to get us to negative 1.6 times 10 to the 5 joules. You have to do negative g mm over r twice if you want to do this question correctly. And we did once for each of those numbers on the previous page. You can't use negative g mm over r one time and expect to get the right answer if you're lifting it from one altitude to another, if you're not going all the way to infinity. So a little subtraction here. What would that be? We're going to get like a 0.4 times 10 to the 5, or I guess it would be a 4 times 10 to the 4 joules, I guess. I'm not even really too concerned about the answer. It's just the biggest issue for me is that you'd have to be doing negative g mm over r twice. Okay, this one's just kind of getting silly, trying to get as much stuff into one story as we can. During a crash landing, the Winnebago descends vertically downward from an altitude of 1,000 meters. Okay, altitude, right? So that's that height above the surface. Some small retro rockets fire in an attempt to slow the descent. Okay, Need to add some fire. So we got some little retro rockets here, firing some flame down. Oh, another little retro rocket here, firing some flame down. The small retro rockets fire to slow the descent. The initial downward speed of the Winnebago is 14 meters per second, and it strikes the asteroid with a speed of 4 meters per second. You have to determine the average force from those rockets. All right, I'm going to use this conservation of energy idea as a big, giant organizer, but I'm going to make some serious changes. Like, for one thing, this MGH, no, I'm going to change that. It's a space question, so I'm going to go negative G, M, M all over R. There is some kinetic energy at the beginning of the story, so I'm putting that value in for sure. There's no work shoving it down. I don't have to worry about that at all, so I'm going to throw that term away. But then on the other side of the equal sign, again, I'm going to switch this MGH out, and I'm going to go with negative G, M, M all over R. We are going to crash land with some speed, so there's some 1/2 m v squared there. And yeah, we've been using some rockets to try to stop this motion from happening, so there's going to be a force of friction times distance in this story. Now, I'm not even really all that worried about the answer, which I think, by the way, is like 580 newtons. I'd rather kind of spend a moment or two to focus on what numbers go where. This R value, when you do negative GMM over R, the R value is how far you are from the center. So this Winnebago would start 5,000 meters away from the center. That would be the number you'd have to put in for the R. This is when you first start your descent, so your velocity here would be the number they mentioned at the beginning, 14 meters per second. And then I get to another negative GMM over R. This is the value for R, how far you are away from the center when you're done. Well, you're not at 0. You're still 4,000 meters away from the center. You're going to touch down with a V that's apparently 4 meters per second. And the D. The D is actually how far you've displaced, how far you've gone. So you've gone from 5,000 from the center to 4,000 from the center. You have actually gone down 1,000 meters. And yeah, okay, if you really want to know, I think the answer for this force of friction, this backwards force from the retro rockets, is 580 newtons. I got to be honest, I don't really care too much about its value. Just kind of looking at how it all fits together. And what's neat is this organization that the equation gives you, right? It tells you exactly where to put everything. You got your before and your after. Forces trying to make things go faster in the direction they're going, and forces trying to make it go slower on the right. Next question. Stolen this one off of an old exam. A cyclist is traveling at 10 meters per second, applies her brakes, and she stops in 25 meters. The graph shows the magnitude, the size of the braking force, the bad backward force, right? Versus distance traveled. Okay, that's interesting. Her braking force is not always steady. It's not always 160. It actually drops off. You have to find the mass of her and the bike. Okay, so this question to me, it doesn't sound like a collision. This question to me sounds like some sort of work and energy story. I am right away interested in this graph. I see that actually it's a force of friction that they've got there. It's like a bad backwards force. That force is not steady. So I'm going to use this idea of finding the area in order to say that that's equal to work. So in this picture here, the overall area of that graph is actually the work out. It's all of the energy coming out of the story. Now, it's not a complicated shape. It looks like a rectangle and a triangle. So I'm gonna go find that area. It looks like we've got a height of 160 multiplied by a distance sideways of 15, and then there's a triangle. So we go 1/2. The base looks like it's 10, and then a height of 160. And I tried that out a little bit earlier, and I found, okay, look, this is 2,400 plus, and this part here is an 800. Okay, so we've got 3,200 joules. That's the work out. That's the heat that all those brakes are going to create. And now I'm going to use work energy in order to organize this. So yeah, I know on the formula sheet I've got this big, long equation. There's nothing wrong with taking an extra second or two. You're going to have time on the final to do this. Just writing the whole thing out. And then I'm going to go through and decide, well, what do I need and what can I toss? Okay, the first MGH. Was she up high on a hill at the beginning of the story? No. Was she going fast at the beginning of the story? Yes. Keep the 1/2 mv squared. FAD, was she pedaling, trying to go faster? Probably not if she's braking, so you can throw that away. MGH, did she go up a hill to stop? No. 1/2 mv squared, was she going fast at the end of the story? No, she stopped, so that goes. And then there's this term, which a lot of people, they just call this term the heat term, right, as we unload all that energy. And we found that number, it's 3,200. So the solution to this is going to be 1/2 mystery mass, starting off with a velocity of 10 squared, equals, now here comes that last term. You don't have to multiply by distance again. You've got the number. It's 3,200. And so you just go with that 3,200 as being the value for force of friction multiplied by distance. I got to be honest, I don't even know what the right answer is. I don't really care, actually, for this review. I'm just trying to figure out ways to get organized, and conservation of energy is definitely the way to go on this one. Number 5, also stolen off of an old exam. A ball is thrown at 15 meters per second towards some barriers. In which case does the ball experience the greatest impulse? Impulse. Okay, so impulse, that's force multiplied by time. I guess some sort of, backwards force from the barrier multiplied by time. Well, you know what? You tell me the force and you tell me the time and I'll go figure that out. But they don't want to. Nobody is telling you the number of newtons or how many seconds it gets pushed for, so we need to cheat. I know that the impulse acting on that ball is the same value as the change in momentum, mass times the change in velocity. And I know that change in velocity is just going to be final minus initial. So I'm going to go and do some calculations over here on the right-hand side of this equation to be thinking about how much impulse there must have been. But be careful, because these stories have things going forwards and backwards. And the way that you actually do subtraction with vectors is you add the opposite. So we have to be thinking VF plus negative VI in order to actually come up with the right value here. I think this one is kind of a momentum impulse question. It's one object only. It's not a collision that we're going to do conservation of momentum with, but momentum and impulse is a great way to get into this question here. So I'm going to look at each one of these and see how their values would differ. They all have the exact same value for M. It's the same ball, but they have different values for this bracket, for VF minus VI. The first one, it rebounds back at 2. So if I go to take a look at that delta V, if I go to figure out how much VF minus VI is, I would have here a VF of negative 2 subtract a VI of positive 15. So that's actually a change in velocity of minus 17. Okay, it's a pretty impressive change. Bit of a U-turn going on there. For B, the ball is going to rebound at 7. Okay, so I would have a final velocity of backward at 7, subtract forward at 15. Whoa, this is a bigger U-turn. This is negative 22. For C, it just sticks and doesn't move. Okay, so then its change in velocity would be final velocity of 0, subtract 15. That's going to be negative 15. It's not as impressive as the last one. And for D, the object breaks the window and just slows down a bit to 10. So its change in velocity would be final 10 minus initial 15. Oh, its change in V is only minus 5. It just drops a little bit. So I look around and go, okay, well, which one's got the best value for change in velocity? And that's this one with the best U-turn in there. I definitely go option B on this one. This one's really emphasizing that U-turn issue. You could graph, actually. It is a totally separate issue. It's a little trivia, really. But you could be graphing the force acting on that ball and time. And you'd probably find that when it does bounce off that wall, the force might kind of grow and then diminish as it elastically bounces off. And even if it's a weird shape, this area underneath here on a force time graph, that area, it would equal that impulse. It would equal force times time. So it would also, in this story, be equaling mass times that change in velocity of 22. That's just a little trivia thing down there at the bottom. Not really anything we need for this question specifically. Next page, question number 6. This is a neat one because it's actually got both halves of the chapter in it. It was that railroad car that collided with a stationary one, so there's a collision, and then afterwards the train goes up the hill. Key thing to remember here for collisions, momentum is your friend. When these trains collide, I'm just going to put them here now as a little combined train, these various train cars, they're stuck together. During that collision process, there is going to be a serious amount of heat coming off. And that's what kind of stops us from doing just conservation of momentum, conservation of energy, and saying, oh yeah, let's just do that, it'll be easy. You don't know how much heat comes off, so we can't just do an energy calculation for this. We actually have to start off doing a momentum calculation because momentum's your friend. It goes right on past this heat issue and just doesn't care about it. So I'm going to do that over here on the left. I'm going to say, okay, the sum of the momentum initially has to equal the sum of the momentum finally. It's not two-dimensional. They just collide in a line on the ground, so I don't have to do any crazy triangle stuff. But I do have to think about p-values. So the first one, it's got a mass of 0.25 and a velocity of 3. There's the p-value. The second car is waiting. It's got no momentum. And then afterwards, they stick. It's an identical car, it hits. So it's a 0.25 plus a 0.25. We're up to 0.5 kilograms. And it's going to have some V. I'm talking about this V right here, right after the heat's come out, but before you've gone up the hill. And that velocity, after the collision, we got through it with momentum because it's our friend. That velocity is 1.5 meters per second. It doesn't matter whether you have good wheels or not. There's some heat coming out if those things are going to stick together. But now if you do have good wheels, now you can go and do an energy calculation to figure out how high it's going to go. You can quietly roll up the hill. You can take some 1/2 mv squared and convert it into mgh. Both m's are the same here. They're the m's for the combined train. You can scratch it off because it's the same on both sides, or you could put it in if you want. You go 0.5. Speed of 1.5 squared. And then that's going to equal 0.5, 9.8, and the h. Oops, don't even actually know what that number is. Everything's going crazy here. Don't know what that number is, so I'm just going to figure it out for you real quick. So half times 0.5 times 1.5 squared divided by a 0.5 and divided by a 9.8. It's going to go, well, not very high up at all, just 0.11 meters up. So for collisions, you definitely want to rely on momentum. If it's just a nice little roll up and down a hill, then you can do energy. And that question's got everything. It's got them both. Number 7. 5 kilogram object. Okay, yes, that's this one here. It's traveling at 1.6 meters per second. Yep, weird angle. It's got a collision going on here with an unknown mass. So I don't know what this one is. And it's traveling at 2.5 meters per second. They stick together, and kind of weird, they go exactly to the right in the diagram. And you have to find the mass of object M2. So apparently, well, for one thing, it's a collision. Momentum is your friend. So we're going to do this thing for sure using momentum. But apparently there's exactly the same amount of vertical momentum in each ball, and then they hit each other, and those vertical momentums add to 0. But it is a collision. I'm going to try and see if I can do this two-dimensionally with just a momentum triangle. It's only got three different momentums in this story, two before and one at the end. So I think we can do it by doing a triangle. I think it's actually going to work out pretty well. So in the end, we've got one nice clean momentum going this way. I'm going to draw that final momentum in here. And at the beginning of the story, we've got two separate momentums. That mystery mass, mass 2, is actually kind of going up and to the right. So I'm going to draw that one in here first. This is momentum 2 initially. And momentum 1 initially is going down like that. Probably no right angle in this story either. So there's momentum 1 initially. All right, what else have we got? There's some angles there. This 28 degrees, it looks like it's the angle between object 1 and things that go flat. Well, here's object 1, and this blue line is flat, so this is 28 degrees. The 21 degrees is between the mystery mass and things that are flat. The blue line is flat. Here's object 2. So that's 21 degrees. You know, there's only 180 degrees in a triangle, so you've got 49 degrees already. There's just 131 left, just subtracting from 180. This next issue is really important. It's not hard, but it's really important. When you go to conserve momentum, and you go to use one of these triangles to actually do that conservation for you, which is nice, you have to be working with p-values. So this original momentum for object number 1, it is not 1.6. It's actually 5 for the mass times 1.6. It's actually 8. You have to work with p-values. Okay, now I'm just going to go and use the sine law. I can see that that 21 degree angle is opposite that 8, and I'm going to use the 28 degree angle because it's opposite the momentum for number 2 originally. I'm not even going to really finish this question off entirely because I think the tutorial part of it's pretty much wrapped up. I could go sine of 28 divided by momentum 2 initially and say that's got to be the same thing as the sine of 21 all divided by 8. You are absolutely able to find the momentum for object number 2 right now. And if they're saying, oh yeah, that's nice, but you have to go and find the mass. Okay, great. Take your answer from here. That's the momentum. Then you can go and drop that into this. You can say object number 2's initial momentum is equal to the mass of 2 times the velocity of 2 initially. So you can put that into that left-hand side. We know that this number they told us is 2.5 meters per second, and then you can go and you can find this. That's not a big deal. But you absolutely must work with p-values when you go to do these triangles. Can't work with just the velocity. Now the last two. This one is definitely a Physics 12 question, not a Physics 11 question. I've got a car, it's going to collide. Okay, so I'm picking up on some keywords here. It's colliding, so I'm going to be doing, nope, thanks Microsoft. It's colliding, so I'm going to be doing momentum and impulse. It sticks, okay, great, that might help me out here a little bit. I also noticed that it's two-dimensional. This car is going west, and the van is going to the south. So I have to respect that two-dimensionality. I'm lucky that they stick together, and I think I can actually get this all done with a picture. Because it kind of looks like this, right? I've got my 3,000 kilogram van going to the south at 8, and it's going to collide with a 2,000 kilogram car mentioned at the beginning of the question going back to the west at 5. It's 2D. Like southwest, like it's bolded and everything. It's 2D, so we have to go and work two-dimensionally. You can't just go and do a grade 11 calculation on this. So it looks like this. You've got one momentum initially going this way, that's your car. And then you've got another momentum going down to the south, that's your van. I'm going to go and find those p-values in a second, but then they stick together and they become one big diagonal momentum altogether. And you have to find the velocity, right, for those things afterwards. Okay, you got to go with p-values again. Got to do masses times velocity. So 2,000 times 5, this is 10,000. The units are, kilogram meters per second, right? We're multiplying m's and b's together. Up and down, 24,000. The total, not 34,000. You got to do some Pythagoras. If we do some Pythagoras, we can find that momentum and we can find the angle in there, right? So that final momentum, a little Pythagoras, it'll be done quick. That final momentum is actually 26,000 kilogram meters per second. If you want to know velocity, then you've got to say, oh, okay, that mv is actually 26,000. And the mass is now some combined crazy blob of metal. It's 5,000 kilograms big if I put the two masses together. All right, so the velocity is 5.2 meters per second. That's most of the answer. Velocity is a vector, so we really should do trigonometry as well to get the angle. So tan of that angle would be the opposite side, 24,000 divided by the adjacent side, 10,000. And I think the answer for that is like 67 degrees, I think. So my final answer, if I've got this right, would be that the velocity of the combined mass, 5.2 meters per second, 23 degrees, sorry, not 23, 67 degrees. Try that again. South of west. Final question. Determine the amount, if any, of heat that's released during that collision. Okay, well, it was a collision, and in question 8, we went with momentum. It is your friend for collisions. It's the first thing you should go to. But now they're saying, well, what about heat? Okay, now I'm going to go and do work in energy. Now I'm going to take a look and see if I can find any missing joules of energy there. There's no MGHs, but at the beginning of the story, there's a 1/2 mv squared for the car, and there's a 1/2 mv squared for the van. Afterwards, there's a 1/2 mv squared for the big mess that's all together. And there might be some heat. No MGHs to worry about. The neat thing about energy is it doesn't care about direction. It's not like momentum. So we're just plugging in some numbers with no care for which way they're going. Car was going 5. The van is 3,000 kilograms. It was going 8. At the end of the day, we have got 5,000 kilograms going 5.2. And there might be some heat. Well, you run the numbers, get 25,000 joules of heat here, got 96,000 joules of heat there. Afterwards, there's a pretty good amount in that combined vehicle, 67,000, and there's still, I'm wondering, might be some heat. And sure enough, in the end there is. The amount of heat that had to be given off during this collision is 53,400 joules. Okay, couple of issues. 3 actually. 1, because there is heat coming off, because the heat is not 0, this is an inelastic collision. That's all about whether heat came off or not. Second issue, okay, technically we kind of knew that there would be some heat because if they stick together, when they stick together, there's always heat coming off. So it'll always be inelastic for sure. Third thing, if you had just been given the request in question 9 to find the heat and you weren't asked to find the velocity back in question 8, if you were not asked to find this 5.2 number up here, find it anyways. If you're asked to find how much heat there is, you really need that 5.2. And to find this 5.2 number here, you've got to rely on momentum. It's your best friend for collisions. Get that done first. Then if people are asking you about energy, then you can go and do those energy calculations. And this is the end of the third video.